Okay, hi everybody. We are continuing on with section 10.1 of chapter 10. This is the torque section, and this is part B of my lecture on torque. In part A, we talked about how to calculate the magnitude of torque, and in part B, we are going to figure out how to figure out the direction of torque. Okay, so we learned in the previous section that torque depends not only on the force, but where the force is applied. So how are we going to capture this using a single vector? So the way we're going to do that is with the right-hand rule. Okay, we've learned about the right-hand rule in chapter 1 when we learned about the vector product or the cross product, and we're going to do the same thing here. So to calculate the direction of our torque vector, we're going to do r cross f using the right-hand rule. So the right-hand rule is as follows. We point our fingers in the direction of the r vector. Okay, then we curl our hand in the direction of the force vector, and then our thumb is going to point in the direction of the torque. So if you have a vector A and a vector B and we want to calculate A cross B, I point my fingers in the direction of A and then I curl them in the direction of B, and now my thumb is kind of pointing out away from the page. Okay, and we sometimes denote that with a little dot, meaning it's like an arrow coming at you. Right. The thing that's not correct here is this A cross B. I cannot point my fingers in the direction of A and then curl them towards B. Or if I did, it would be going the long way around. And so that's not what we want to do. We want to do the closest direction. A cross B, curl my hand from A to B. Right? And if this was right, it would be this symbol is an arrow moving away from you. It's like looking at the feathers on the back of the arrow. Right? So this would be into the page, but this is not correct right now. The direction of this torque vector is out of the page. That's what the right-hand rule is telling me. Okay, a couple more examples here using our wrench example. Here, this is my vector r, again, from the axis of rotation to where the force is applied. Here's my force vector. If I do r cross f, the only way I can curl my hand in that direction is if my thumb is pointing into the screen, into the page here. Okay, so this has to be three-dimensional. If this is my xy axis, then torque is going to be in the z or negative z direction. Okay, with this wrench here, r cross f, the only way I can curl my hand in that direction is if my thumb points out of the page, right, coming out of the screen right now. And in this case, I have zero torque. I cannot curl my hand from r cross f. So when you have two vectors which are parallel, that produces zero torque. That's what we've already learned about the cross product. Okay, but to really picture this, we have to think a little bit three-dimensionally. So let's go to this example. We have a wheel. The wheel is spinning on the xy plane entirely, right? And I have a force applied at the edge of the wheel in this direction, and it's applied at some distance from my axis of rotation. That's my vector r here, right? So if I want to calculate r cross f, I again point my fingers in the direction of r, curl them in the direction of f. The only way to really do that, you have to twist your hand around a little here, is that the cross product is going to point down. In this case, it's going to point in the negative z direction. So we're going to call this negative torque. Okay, negative torque is going to result in negative angular acceleration. So this force is going to start this wheel spinning. It's going to be changing the angular velocity of this wheel, and it's going to cause negative angular acceleration. We can also check that we're going to get negative angular velocity by, again, using a different right-hand rule. Curl your hand along the direction, curl your fingers along the direction the wheel is now spinning. It was initially not spinning. Now it's going to be spinning in this direction after you apply this torque. Curl your hand in that direction, and your thumb is going to point down, again in the negative z. So this net negative torque is causing negative acceleration, and therefore it's going to result in negative angular velocity. Okay, so if I want to draw on the torque vector, it'd be some vector down in the negative z direction. I drew it up here because it's kind of hard with this picture to draw it. Okay. If I apply the same magnitude force but in the opposite direction, I am still going to get a torque, and the direction of the torque is now going to be the opposite direction. If I do r cross f now with my fingers, my thumb is going to point up. All right, so that's positive torque. It's in the plus z direction. This torque is going to cause positive angular acceleration. If this wheel was initially not moving and then I apply a force in this direction, I'm going to give it positive angular velocity, and it's going to start spinning in this direction. Again, using the other right-hand rule, curl my hand in the direction that wheel is spinning, and my thumb is again also pointing up. All right, so we have two different right-hand rules now, one for the cross product and one for angular velocity. Okay, so if I want to draw on this torque vector, I just do it as follows. R is entirely in the xy plane, F is entirely in the xy plane, the wheel is spinning entirely in the xy plane, but my torque is not in the xy plane. In fact, it's perpendicular to the xy plane. It's in the z direction. Okay, so it's along my axis of rotation. Right? If this is a wheel, it's along the axle. And just like angular velocity and angular acceleration, those vectors are also always along our axis of rotation. Right? So going from here to here, I'm applying the same force, but I'm decreasing my distance between where my force is and where the axis of rotation is. Right? I'm applying the force closer to the axis of rotation. By our torque formula, we're actually decreasing the magnitude of the torque. Right? It's going to be a less effective torque by applying that force closer to the axis of rotation. And you can see I denote that by making my torque vector shorter. Right? So the magnitude of my torque is getting smaller, but the direction isn't changing. Okay, and this is just a common source of confusion. The torque is in the plus z direction. That does not mean anything is moving in the z direction. All the motion here is in the xy plane. But again, this part of the wheel is moving in this direction, this part of the wheel is moving in this direction, this part of the wheel is moving in this direction, this part of the wheel is moving in this direction. So we choose not to use any vectors on the xy plane when describing rotational quantities. We choose to use the z-axis. We choose to use the axis of rotation to denote these vectors. So torque is always going to be along the axis of rotation. Nothing is moving in that direction. Okay. And again, if I apply a force directly on my axis of rotation, that means no torque. I have no lever arm. I am not getting any torque here. If I apply a force along my radius towards my axis of rotation, I'm also not getting any torque here. Right? The cross product is r cross f, or rf sine of the angle between these two vectors. These two vectors are 180 degrees apart, which means sine of 180 is 0. Right? So our definition of the cross product tells us this is 0 torque, and just conceptually we know this force is not going to cause this wheel to rotate. Same thing as pulling on the wheel. If you pull on a wheel, you do not cause it to rotate. These two vectors are parallel. The angle between them is 0 degrees. Sine of 0 is 0, so r cross f is going to be 0, and that means 0 torque. All right, so our vector definition of torque with the cross product is exactly the mathematical definition we need to describe this, and that's why we defined it in Chapter 1 in the first place. So let's end this video with a quick clicker question. You can think about this on your own. So I'm applying some force at this location. I have 3 different options: force A, force B, and force C. They're applied on some object. This is my lever arm here. Not my lever arm, but this is the distance between my axis of rotation, which is my origin, and where I'm applying the force. So this is my position vector. Which of these 3 forces is going to cause the largest torque? Okay, and you can pause the video. I'll give you a hint. You don't have to do any mathematics necessarily to solve this problem. So you could use one of the 3 torque magnitude definitions to calculate the actual torque for each of these and figure out which one is bigger. But you can also kind of look at the picture and think of it a little bit more conceptually and solve the problem. Okay, so I'll give you another hint on the next page. My advice is to draw a circle for the actual path that this object is going to take. So if this is my axis of rotation, the origin, and this is where I'm applying the force, I'm going to try to move the object along this circle, right, in one of these directions. So this is a circle. Once you draw the circle, it helps you figure out what are my tangential components of the forces. So if I draw on my tangential components of the forces, right, force A is in this direction. A lot of that force is not useful, right? A lot of this component of the force is in the radial direction, and that's just pulling on the wheel, right? This component of the force is the tangential component. Okay, that's the useful part. For force B, it also has some radial component, which is not useful, but it has a bigger tangential component, right? This component is tangential to the circle, and that's what's going to cause rotation. So that's bigger than A. So definitely the torque on B is bigger than the torque from A. And from object C here, this is going to cause rotation in the opposite direction, and this torque is going to be given by, to calculate it, we need to figure out the tangential component of the force, which is this, right? So this component of the force is not useful, right? That is the radial direction. This component of the force is the useful part. That's the tangential component, and that's pretty small here, right? So I can see B has the biggest tangential component of the force. And they all have exactly the same r here, or the same distance between the axis of rotation and where the force is applied. So the force with the biggest tangential component is going to be the biggest torque, and so the answer here is B. Okay, and you could do the math if you want. You can plug in all the numbers for it to figure out tangential component of A. This is 100 Newton force. This is a 30-degree angle, so I need to use sine of 30, or I could use cosine of 60 to figure out the magnitude of that component, and that's 50 newtons. For force B here, that's an 80 Newton force at an angle of 30 degrees, so I can use cosine here because it's adjacent to this angle, so I want to use cosine. When I do that, I get a tangential component of 69.3 newtons, and for force C here, I have this 53-degree angle, which is opposite. This is my tangential component is opposite that angle, so I can use sine of 53, and I find 31.9 newtons. So B has the largest tangential component of the force and the biggest torque here. So thank you.